So welcome to my presentation. In this presentation, I will cover assignment number 4, which is the introduction to flip-flops. So I'm gonna start now. So synchronous sequential circuits are digital circuits which are governed by clock signals. The transition from one state to another takes place only by the application of specified clock signal. So synchronous sequential circuits are also known as clock sequential circuit. So these circuits are used in counter, shift register, and the memory unit. So as you can see, this is the block diagram. This is the combinational logic circuit, right? So what makes the logic circuit unique? Its memory elements present. So these memory elements could be used again for the input, which is the this memory element acts as the a storage device that will store whatever output that was produced before to in order to become the part of the next input. So this is the block diagram for sequential logic circuits. So next I'm gonna move on to the flip-flop. So defining a flip-flop, it is an electronic circuit with two stable states that can be used to store binary data. The stored binary data can be changed by applying varying inputs. Fundamental building blocks. These are fundamental building blocks of digital electronic systems used in computers, communications, and other many types of systems. So as again used as data storage elements, and again it is the basic storage element in a sequential logic circuit. So these flip-flops represent the basic storage element. So its equivalent logic circuit will be discussed in the different types. So different for number 2, different type of flip-flop, and explain each type. So there are four majority types of flip-flops. I'll start with the first one. It is called the SR flip-flop. So this simple flip-flop circuit has two inputs, which are the S and R. As you can see right here, the S and R, the S represents for the set and the R represents for the reset. So S and R, in this system, when you set the S input as active, the output Q would be high and the Q bar or Q prime here will be low. So when S is high, Q is high and Q bar is 0. So it matches the truth table. Once the input outputs are established, the wiring of the circuit is maintained until S or R goes high or the power is off. The two outputs are shown back there are the inverse of each other. So the truth table are as seen in the next slide. So as you can see, this is the truth table. And initially, we have here, right, S and R, no inputs yet, no logic 0 yet. So Q is 0, Q bar is prime. A Q prime is 1 since they are the inverse of each other. So when input is applied to the reset, nothing happens, right? So however, for the set, when we apply input for the set, it will change the Q to logic 1. And meanwhile, for the Q prime, it will become 0 since, as I said again, they are the inverse. So this bottom part, it's the 1 1. For S, what happens now if both set and reset are uh, active high, right? So it becomes invalid input since it defeats the purpose of the latch here. They can't be, it will be invalid, considered invalid. So we have here this infinite symbol right here. It just this this SR flip-flop is the major issue is what happens if S and R are both logic 1. So the invalid input happens because there is no direct output for the flip-flop to discover, because there is the both S and R are high, it becomes invalid. So next, due to the undefined state in the SR flip-flop, another flip-flop was required. So we have here the second type is the JK flip-flop. It is an improvement on the SR flip-flop where S equals to R equals to 1. Both S and R equals to 1 is not a problem. So this is the solution for that problem I presented a while ago. The input condition of J and K equals to 1 gives an output inverting the output state. However, the outputs are the same when one tests circuit practically. So in simple words, if J and K data input are different, then the output Q takes the value of J at the next clock edge. If J and K are both low, then no change occurs. If J and K are both high at the clock edge, then the output will toggle from one state to another. JK flip-flops can function as a set or reset flip-flops. So this is the better the answer to the SR flip-flops shortcomings. So we have here the J and the K right here, right? So we have here the clock input. So as you can see from the truth table, we have here the 1 1 is not a problem anymore since there is a clock running, and the outputs will just toggle right here next the next set of inputs 0 1 0 1 nah, with the next cycle of 1 1. What as you can observe, the output became toggled, it just switched. So this is due to this clock input right here. This solves the problem of the SR flip-flop. This is the very nice advantage of JK flip-flop. Next, for the third, we have the D flip-flop is a better alternative, and that is very popular with the field of digital electronics. They are commonly used for counters and shift registers and input synchronization. In this type, the output can only be changed at the clock edge, and if the input changes at other times, the output will become unaffected. So the change of the state of the output is dependent on the rising edge of the clock. The output is the same as the input and can only change at the rising edge of the clock. So basically we have here the D flip-flop. As you can see, there's only a D input here with the inverter, and then the next connection is the clock. So as you can see, we have here we have here that the Q will not turn on as long as both it must be that both D and this clock offset must be at logic 1, so that the Q will have a logic 1. Otherwise, we have here it is not turning on, right? Because the 0 0 here 1, but the clock is at 0 state, so the Q prime is now still at 1 Q bar, so it just the inverse. So this is for the D flip-flop. Lastly, we have the fourth. The T flip-flop is like a JK flip-flop. Why I said that? Because they are basically a single version input of the JK flip-flops. This modified form of JK flip-flop is obtained by connecting both inputs J and K together. So both J and K together, we have JK here, right? But for this time, for the T, we have it is wired to the single input. So what makes the difference? It has only one input along with the clock input. So these flip-flops are called T flip-flops because of their ability to complement its state and to toggle to complement its state. So basically the output toggles, so hence the name toggle flip-flop. So as you can see, here the circuit, right? So based on the truth table, we have here there is a toggling of outputs, right? So as I understood the table, what happens here when t is at logic 0 initially, we have here to the 0 0 first. So when t is high now, what observe what happens in q remains the same, it latches the same output. Meanwhile, for its inverse q prime, sorry, the input will now toggle to logic 1. So they just basically complement each other. This is why it's called the toggle circuit. Now another next cycle. If t is 0, what will happen to q? This is now the time for the q to be toggled. So we have here q is 1. Meanwhile, q prime operates opposite when t is becoming low, 0, the output is remained the same, it's latched. So what happens if we move to logic 1 for t again? So as you can see, for q, right, it latches, remains the same, and for the q bar, this is the time to toggle. So they just basically toggle each other based on the status of this t, whether it's high or low. So that's all for the four types of flip-flops. Next, we have here applications of flip-flops. So first, I have here the counters, which are widely used in digital electronics and digital systems. They are used to count the number of events occurred at a specific interval of time. Mostly, a counter is used for counting the number of pulses entering at the input of a circuit in a specific time period. So, in the terminology of digital electronics, a counter is a sequential circuit that produces specific count sequence. It is an electronic device which is used to count the clock signals. Counters will have memory since they have to remember the past states of digital circuit, hence they consist flip-flops in this structure. This is where the flip-flop comes. The counters must have memory. So this is the advantage of having flip-flops. The device will, for devices that needs a memory state. Next, application registers. Flip-flops can store a single bit of data. So registers are used to store multiple bits of these data. So flip-flops are used to design registers. Again, this is another application, right? According to digital electronics, a register is a device which is used to store the information given. As a single flip-flop is allowed for 1 bit storage, n flip-flops are connected in an order to store n bits of data. For example, if a computer is to store 16-bit data, then it needs a set of 16 flip-flops. So n flip-flops in order to store n bits of data. So next, we have here frequency division, another application. As the name implies, the frequency divider circuits are used to produce the digital signal output exactly half of its input frequency. So the frequency divider circuits are generally used in design of asynchronous counters. The process of dividing or reducing the output frequency to half of its input signal frequency is called the frequency division. So this means basically if we process an input signal of frequency of 160 kilohertz, then the frequency divider will just cut it to half. It will produce the output of 80 kilohertz. Lastly, last application, the data transfer. It is the process of transferring the data from one register to another register. So the multiple registers are involved. Data transfer, this is where another application of flip-flop. In general, these shift registers perform this type of operations. Data can be transferred by using flip-flops in two ways, which here we have here, serial data transfer and parallel data transfer. So that's it for the applications. So next we have the explain the application of each logic circuit under sequential logic circuits. So under sequential logic circuits, as we discussed, we have here, we have, right, the counter, the shift register, flip-flop. So anything that uses a memory state that needs to utilize its past inputs, they are under the applications of sequential circuits used to build a memory unit. So devices that needs to build memory unit, and as a programmable devices such as PLDs. So PLD stands for programmable logic devices, used to build another component used to build logic circuits. We have here the FPGA. Again, it is a field programmable gate array. So it is an IC designed to be configured. So next we have here CPLD, which is the complex PLDs, right? So it's a more complex programmable logic device capable of performing complex operations. So that's it for my video, and thank you for listening.